This episode was sponsored by Property, the leading real estate agent for all real estate transactions with a comprehensive ecosystem. They combine highly trained experts with the latest technologies on an intelligent platform to provide clients, brokers, and service partners with risk-free, flexible, and simplified services. Learn more at property.com. That's property with an I.com.
Try to find a customer and only one customer and only one use case and only one application and build your hardware specifically for that.
Welcome to the Swisspreneur Show, a podcast about startup stories and learnings from experienced entrepreneurs. If you enjoy listening to our show, make sure to follow the podcast and leave a rating. And now, here's your host, Merle.
Welcome to another episode of the Swisspreneur podcast. Today I'm joined by Imad, who's the co-founder and CEO of RTDT. Welcome, Imad. Happy to have you.
Thank you, Matt, and I'm happy to be here.
So RTDT, you provide site-specific aerostructural data at scale for wind turbines. But of course, the first thing I need to ask you is, what does RTDT stand for? Yeah. And how often does it happen that somebody says R2D2?
Yeah, so exactly, R2D2 sticks in everybody's brain. And usually when people say R2D2, I don't correct them during a conversation if it really keeps it sticky. But RTDT stands for real-time decision tools. The idea behind it is that you're collecting a bunch of data on turbines and then you're providing real-time controls or decisions that needs to happen on the turbine. At this stage, we're not doing real-time, but hopefully in the future we will be doing real-time. Yeah.
Amazing. And we'll get into what exactly it is that you do in a minute. Mm-hmm. Before, I would love to know who you are first. And I know that you trained as an engineer in Canada and Denmark before you moved to Switzerland. Can you tell us about your path, why you chose that path, and then maybe also what drew you to wind energy?
Okay. Yeah, that will go back a while. So I did mechanical engineering and computer science back in Canada, that's correct. And in my final year, that was 2003, 2004. So I'm not very young. So I was finishing and we were having a final project. You know, it's a 6 months real design, mechanical design aspect with a lot of software in it. And as we were finishing, my professor back at the time, he asked me if I would like to do a master's thesis with him on neural networks for gas turbines, so artificial intelligence back in 2003. I said, yeah, okay, I will think about it, to start in September 2004. But in November 2003, I saw a documentary on Discovery Channel. I don't know if you know the Discovery Channel, but it was about Hans Reu, which is the first offshore wind farm in Denmark. The construction, the design. And the first thing that clicked in my head is that, oh, wow, I've never seen a wind turbine before in real life. So it was on TV. And I realized, oh, these are really sexy machines. And what can you do to study those? Because there was a lot of aerodynamics and structural dynamics, and it was really good at that. So I literally Googled Masters in Wind Energy. And the first thing that showed up is the DTU, which is the Technical University of Denmark. So and I think it was December, I applied just like this. Yeah. And then in May, I got the acceptance. In May, I graduated from my university in Canada. And in August 2004, I was in Denmark doing my Masters in Wind Energy. So this is where actually it started, really. It was just a lucky shot, and I was searching for something different. But imagine if I had accepted this master's thesis in neural networks with my professor. True. Probably I would be the god of artificial intelligence by now. And Elon would be hiring me or something. But so in Denmark, so 2004, 2006, I was doing my master's thesis. And my thought, I would be going back to Canada to do something. But then I applied to a job at Vestas, which is the largest manufacturer of wind turbines. And a few weeks later, in 2000, that was probably summer 2006, I got a call to come for an interview. And I forgot that I actually applied. And then they said, what is this about? I was okay, fine.
Who am I speaking to?
Yeah. And 4 hours later, I was on a train up. It was very old. It's a small village up in Jutland in Denmark. So I got accepted. And in September 2006, I think, I started at Vestas. And there I was doing design of turbines. I was working on loads, aerodynamics, and control simulations for 2 megawatt, 3 megawatt turbines back in the day. And I did this for 8 years approximately. And then I went to do my PhD. So I worked for a long time before I did my PhD in also in wind energy, but this time it's on probabilistic modeling. Using uncertainty quantification for the assessment of safety factors on turbine design. And one thing led to the other, and my professor at DTU knew a professor here at ETH. I went for a secondment for 6 months, who invited me back for a postdoc, and that was in 2015 when I moved here. But the reason why I moved to Switzerland is that because my girlfriend back then, so we met in 2010, she's Swiss, and in 2015 we moved here because she was pregnant, we were having a baby, and now we have 3 babies. And I've been here for 10 years. I live in Basel, by the way. Yes.
Super cool story.
Yeah.
So at what point in your research did you realize that you could solve a real problem with things that you're working on?
Yeah, so after working for a long time as an engineer, let's put it this way, in the industry, and you get your hands dirty, you know how to take shortcuts, really solve a problem and not take it to perfection every single time. A lot of problems start showing up where there are no real solution other than quick, dirty shortcuts and some design recommendations that you have to follow. But you don't really understand the background of many of these things. And that was the thing that led me to my PhD. And whatever I did in my PhD actually ended up in the design standards now, in one way or another. But then what I did at ETH in my postdoc, because I stayed there from 2015 till 2024. And there I did a lot of work on structural health monitoring, so developing models for monitoring the health of the system, of the turbine. And then part of it was the AeroSense system, where it was a project at ETH where we were designing and developing the hardware and the software for the AeroSense, which is the product of RTDT right now. And this is where we realized actually this is really a thing that can go from a research to technology to a product, because nobody measures aerodynamics in the field on turbines right now. It's a very difficult problem. So we thought, let's do it. Nobody's solving this problem. We can try it. It's difficult, but why do what everybody is doing? So let's take a chance. So I quit my job, and then we spun off with my back then colleague who was a PhD student, and then he's now with me as a co-founder.
What would you say was the toughest part, moving from like a lab prototype to an actual product that would sell?
Yeah, you discover very quickly. I mean, so maybe we didn't talk about what RTDT does, but we do a lot of hardware. And doing hardware is not a very obvious thing for a lot of us who, let's say, did a lot of software, and all of a sudden you need to do hardware. So taking it to an actual product, you need to take care of supply chains, of field maintenance, of deployment, of simple logistics of shipping a piece of hardware to somebody. We have batteries in it. How do you deal with batteries at customs, etc.? But really, taking something to industrialization, to productionize it, is not very easy at all, especially when you get to scale. So you can go from some kind of a researchy thing, you write a hacky firmware for your hardware to work, then you put it in a test environment just to write a paper, and then you forget about it. Then when you spin this off to make it as a technology and develop it, you realize this is all crap, and you need practically to start from scratch. And this is what we did. I mean, me and my colleagues and my engineers, we spent probably the last 8 months on rewriting all the firmware, redesigning all the hardware, because we know what you took from university worked for that purpose.
In that context.
And now all of a sudden you need to redesign it for manufacturing, because when somebody looks at this, there's a lot of manual work. This is not manufacturable, and we need to change a lot. The material used will not survive for more than a few weeks. What was good for our tests, which is very awful for whatever we want to sell. And then the biggest, probably after the manufacturing aspect, is the validation. Because whenever you talk to customers, great, we love the value proposition, but can you show that this worked? And in our case, it's not obvious that you can go on a turbine in the middle of nowhere, organize it, that you can put something on 100 meters up in the air. And then we're measuring stuff, so measuring aerodynamics, that nobody measures. So how can you validate stuff that nobody measures? It's
cannot compare it.
We cannot compare it. So we have, of course, a lot of simulations. We have wind tunnel setups. We have controlled environments where we can show some aspects of it working. And this is why part of our work right now is to do what we call co-developments with wind turbine manufacturers. So really develop certain aspects that are of interest to them, specifically something related to controls, and then validation. which we would need access to a lot of turbines. And this is where really we could shine in a way.
And how exactly does it work?
Think of, people are listening, so...
Let's describe it.
So think of it like a very thin, flexible patch where embedded inside there are a lot of electronics, so a lot of sensors. So we could measure up to 60 channels. This patch, like your medical patch you put on your skin, but in our case, we put it on a turbine blade with a tape, literally, that you stick it on the blade, and it measures aerodynamics, meaning it's measuring, like on an airplane where you have your wings, and on the wing there are lift being generated. So we actually measure the aerodynamic pressure generating this lift, because it's a very essential feature of the efficiency of wind turbine blades when they're producing energy. We also measure the kinematics. So think of it, anything that you can describe in meters per second, or meter per second squared. So deflections, deformations, twist, pitch, RPM. We measure all of those as well, or we infer some of them. And we measure some structural aspects. Let's say what we call, operation model analysis. So we can tell you what the frequencies and damping and mode shapes on this very long blade. And think of the blades as something which is very long, slender, and up to 100, 150 meter long. One blade. So making the aerodynamic assessment is not very easy. So we are probably one of the first ones who are doing this right now. So you stick this patch, it's completely wireless. So there are no wires coming from the blade anywhere. And it's communicating via low power, long range Bluetooth. And it's self-powered. So we have a solar system that is powering the patch. So that's on the hardware side. And on the software side, we use all of this information to infer specific aerodynamic features like angle of attack, relative wind speed, aerodynamic efficiency, aerodynamic load, aerodynamic distribution, because we will have this patch distributed at least at 2 or 3 locations along the span of the blade.
Along one blade?
Along one blade. And at the moment, we have 8 patches on one blade.
Okay.
So in the future, we could have more on more blades, but for now, we stick for one blade. It does what it needs to do. And then from the aerodynamic and the structural data, we are building let's call it an optimization plugin that interfaces with the control system of the turbine to tune very specific parameters to boost annual energy production.
Okay.
So at the end of the day, what this patch will do as a value proposition to the customer is boosting annual energy production on their turbines. And if you think, okay, how much money is that? So anywhere from 1 to 5% increase in annual energy production doesn't sound like a lot, but imagine you have a remaining lifetime on a turbine 10 years. And if you discount it over, let's say, on a 8% discount rate, then you're talking about anywhere from up to 100K to $1 million in net present value per turbine. So if you're a very large owner, and there are many with hundreds, maybe thousands of turbines, it starts to add up. So our value proposition is increasing the annual energy production of the machine, increasing the net present value or the revenues of the owner and operator. So we operate really in increasing revenue and not on saving on maintenance or service. Because for us, if you're a turbine owner and you sell a kilowatt hour for, say, 15 rappen or 5 rappen, it doesn't matter. And you know that you have a contract for the next 15 years for that amount. The more you produce, the more revenues you will make. So you can very easily calculate what our patch assessment will provide you in additional revenues in the future. But if I promise somebody to reduce their costs on maintenance, it's not very concrete. I cannot promise the same savings over time, especially that machines get older, so they will need more maintenance and services. So that's not constant. Whereas machine producing energy is more or less constant over time. You can always retune the control system to push it a bit more, especially towards the end of life of the turbine. So this is the technology, the product, and the value proposition for RTDT.
What is the most common issue or problem that you see with your data that the providers then can tweak?
So there are probably 2 very important aspects. One on the structural side, and that's related to the blade deflection.
Yeah.
So usually you design a blade structurally for a lot of deflection. I mean, they deflect a lot. We're talking about 10, 15 meters sometimes of blade deflection on a 100 or 150 meter blade. And you need to design them in such a way they don't hit the tower because they're passing by the tower. So there's a design limitation there. So that's one thing that you can measure in the field, and you can say, well, these blades are designed to deflect this much. on this site specifically, they're not deflecting this much, meaning that you can push these turbines more. So if you can push more, producing more power, you can deflect them more to their designed operating conditions or design envelope. So you can then extract more power. The other aspect is aerodynamic, where the turbines are supposed to operate at an optimal, what we call angle of attack. So that's the angle at which the air is attacking or hitting the blade. And if that's, usually you design it with some kind of a conservatism. And if you know how much you're conservative in your design, so that you don't go into stall or increase the loading on the machine, you can measure it site specifically with our patch. And you can then recommend you're too conservative, and you can add an extra degree of aggressiveness, let's say, on the control system. So you have at least 2 or 3 parameters that you can play with to boost energy production. And here in that way, you're talking about 1, 2, 3, 4, maybe more % of energy production on the machines. Typically, it's about 2%, 2 to 3%.
Mm-hmm. Is it usually first like that you upgrade an existing system, basically, or do you rather integrate it into new ones?
To scale, we need to be on the factory floor. You're integrating essentially when the blade leaves the factory floor, these patches should be there. We're not there yet, clearly, because a big manufacturer could be producing 3,000-4,000 blades a year. For me to do 3,000-4,000 blades in the field, it would take me a lot of time, a lot of people. But for now, we are retrofitting in the field. So on existing turbines. Yeah. So there's a lot of friction. You need to find the technicians, stop the turbine at the right time. The technician should be on the turbine at the right time, either on a crane, not often, usually they're rappelling down ropes. Mm-hmm. So they're sticking up 100 meters up in the air. And we install it. It takes about a day to do one blade, more or less. So if you are a big manufacturer and you're working with us, you will have a lot of technicians, a lot of service crew. You can identify all the turbines which are not performing, and then you can deploy this as a program. Typically on wind turbines, every few years you have a inspection program for the blades. So it's not that we necessarily are taking extra time from service technicians, but they can schedule it around the time when they actually really need to be on the rotor. And this is another reason why we work with OEMs, because they have access to all of this information and all of this infrastructure and all of the logistics actually behind it. And by the way, turbine manufacturer, they don't only sell turbines, but they sell service contracts, meaning that they sell you a crappy turbine and they ask you to service it on your behalf. So, and they have something like 50 to 60% of the service market. So they have access to the customers and the capacity to install our products as well. Yeah. So in that way, for now, it's retrofitting, but I hope that will not be for the long term. So our plan is that once we do these kind of co-developments with the OEMs, the idea is to be also on the factory floor with them. Because if a blade goes out of the factory floor, you can imagine it's already retrofitted. When you turn it for the first hours, literally in the field, you can get already an assessment about will this turbine actually be performing as expected? Because you go to the bank and ask for money to build this wind farm. So you're paying a loan. So they need to know their return on investment. So if we can give them this assessment and already tweak from the first year, then you don't have to wait for much later to figure out, oh shit, my turbines are not performing as they should.
And how long would such a patch last?
So in our requirements, it's supposed to last for 12 to 18 months. But the actual assessment that we're aiming to finish within 4 months. Okay. Because imagine if you're doing an assessment for 12 months, then you need to change the control system parameters and wait for the results to show that the annual energy production has changed. We're talking now more than, let's say, 12 to 18 months. Nobody wants to wait for that long. Mm. So if you can do it in 3 to 4 months, the assessment, and within the next 3 months with some clever operation of the turbine, you can show that the annual energy production had actually been affected because of us. Mm. Then within 6 months, you start getting your extra revenue, so you don't have to wait. So, which puts, and this is another reason when you're at university, you think I want something that will last for 5 years, but then you go talk to your customers, try production. If this thing needs to live for 5 years on a blade, the materials I have to use, the electronics will have to be completely different. So the reliability will be completely different. So the cost will be different. Cool. So it makes sense for a few months and then you're out.
Where are your customers? Like, are they located in very specific areas? Mm-hmm. Because I could imagine Denmark, for example, is a big market.
Yeah. So if you think about who are our customers? Our customers are the manufacturers of turbines. There are hundreds of owners and operators, and at the moment, I don't care. We care about the OEMs for many, many reasons. And they are in the Western world, let's say between Europe and the United States, it's only 6. And the other big ones, other 6, they are in China. So, and where in Europe, it's Germany and Denmark.
Yeah.
And the US. So it's, I don't have a lot of tripping to do. I can just travel to 2-3 countries and that's it.
Yeah.
And then at the moment, we're not working with any Chinese colleagues, but probably that should be in our future very soon. You cannot leave 50% of your market just hanging. It doesn't make sense.
That's crazy that it's just 6.
Yeah, it's good and bad because it's very concentrated. Especially if I worked in the industry for a long time, so I know many of the people who know how to use our product or validate it or understand the value proposition. So we don't have any salespeople in the company. I'm practically the salesperson, and so I go to each, and we work directly with the, let's say, the specialists, and that's our entry point, and that's how it works.
Talking about your team, can you take us back a little bit, because you already mentioned that one of your co-founders was already a colleague. How did you meet your co-founding team?
Okay. So, with Konstantinos, he's my co-founder. So he was at ETH with me, clearly, and we were working on the same project. And I liked him a lot, and he's a very clever guy. And I come from a wind energy background. He comes also from a mechanical engineering background with a lot of specialization in stuff that we do right now. So we overlap quite a bit. And then my third co-founder, Aris, he was a VC. And he actually interviewed me for an investment, which he didn't do in the early days. But then eventually he talked to me, kept in touch, and eventually joined me in the company. And he's the chief operating officer and also taking care of all the financial stuff in the company. He's been very, very great. So I'm acting as a CEO. He's acting as the chief operating officer, and Konstantinos, he's the chief science officer. So this is really the main founding team. Of course, big credits also will go to my professor at ETH, Eleni, who actually agreed to spin off this from ETH. She is officially a co-founder, but of course she doesn't work in the company. She's a scientific advisor with us, and she's very, very helpful in many ways. And she advocates for us quite a lot whenever our technology fits with stuff that she's hearing or people approach her for something similar.
Yeah.
Kick Fund is the venture capital firm that invests in Switzerland's best deep tech startups right after they graduate from the Venture Kick competition. Kick Fund has the largest and most diversified deep tech portfolio in the country, which makes it practically an index fund. For startup founders, Kick Fund is the easiest VC they'll work with.
What was the process like of spinning out of ETH?
I think it was incredibly easy. They're very, very helpful. If you communicate very clearly your intentions, what you want to do with your professor, what do you want to spin off, what are the IP issues, how do you want to commercialize things, who you want to take with you. If you communicate very openly, very clearly, very intentionally, they were extremely helpful and very encouraging. And then the rest is on us to make sure that we go register a company and do all the paperwork. But from an ETH perspective, from all the practical issues related to the technology and the IP, they're very responsive, very helpful, and very quick. As long as you on the other side, and that's probably for anybody from ETH who would like to do this, just really be open about what you want to do, including the technology and the IP.
And is the industry highly regulated? Because I could imagine there's also especially like safety critical.
Yeah. I mean,
right?
the wind industry is it's an energy industry, so it's a critical industry. It's very distributed. And it's very, very highly regulated not only from a technological point of view or product point of view, everything needs to be certified. So if we change any parameter on the control system on a turbine, it has to be looked at from a regulatory point of view if they need to recertify anything on the machine. So that's another point of friction potentially for us in the future. From a safety point of view, you cannot even approach a turbine unless you have a big bucket of certificates that you can work on a turbine at heights. So you need to take a lot of training to do it. And of course, I've done it. I've been on many turbines, on cranes, never on a rope, on a blade. I don't think I would do that. It's a bit scary. But yeah, it's very regulated. So at the moment, a lot of the liabilities or warranties are taken up by the our project partners from the OEMs.
Okay.
But sooner or later, we will have to go through some form of certification procedures. Not only on a low level, let's say CE certification or UL certification for electronics, but also if you want to operate stuff on a turbine, you need to ensure that they are safe enough. It doesn't go flying, for instance. So a lot of accelerated lifetime testing will have to happen. You need to show all of this for approvals before you can say, now I can sell, 2,000 of those. Because whoever installing is me or people who know it, who are familiar with the system. But then in the future, it will be out of our hand. We need to have very good instructions, and the warranties will have to come with it. So you cannot guarantee every single time that the installation procedures happened exactly as you wanted it to.
So there's also a question at what point you install the patch, if it's like an already existing turbine versus a new one that's being constructed.
Yeah, correct. I mean, at the moment, everything in the field, I do it, me or my colleagues or people we know, with the OEMs, with the specialists from the OEMs, also on the factory floor. But with the, if you send it to somebody and they say, we will install it according to your instructions, this is also another part of the industrialization and productionization of your system. That not only how do you design it for manufacturing and then manufacturing, but then everything which is downstream in the field, in the installation, in the maintenance, in the manuals, in the instructions on how to do what to do. This is a very painful thing when you deal with hardware.
Yeah. And we, of course, also want to talk about financing, which is, I think, especially interesting for hardware. And you recently closed a $4 million round.
Yeah.
When you pitched to investors, what part of your story or technology made them want to be on board?
Okay, let me put it this way. Probably 90% of whoever we pitch to, when they hear the words, the hardware, they have a painful heart attack and they want to go and they want to go away. Because the majority of investors, especially in Europe, they don't want to hear about hardware. In the beginning, I was just, why the hell are they thinking like this? What's going on? But then now we know, because we are in this process, and lead times are long. It takes a lot of iterations to get it right in manufacturing and distribution. So in a way, they are reasonably correct. But then with those who clicked with them, either they come from some industrial background, so they know the effort that goes into manufacturing, so they internalize, they understand it, and then they understood the value proposition of the product itself in terms of being one of the early ones to do aerodynamic measurements for boosting energy production. So the value proposition was very clear, and we could not demonstrate the full value, but demonstrate working prototypes. That's very important for them. So these are two aspects that some, a VC or an investor, whoever that might be, that understands that how manufacturing is difficult. They come from such a background and they understand the value proposition. And we were very lucky with Swisscom Ventures, who invested in us. So they are the lead investor, and they really understood the potential difficulties with hardware, but the very nice aspect of the aerodynamic measurements, wireless aerodynamic measurements, and the value proposition for energy boosting.
Yeah. What are the most common discussions you have?
The most recurring question is our sales cycle.
Yeah.
Because you have hardware that you need to get it ready, and it's a concentrated market in our case, so you need a lot of hurdles to cross. It's a very regulated market, so you need to ensure all the certification and safety. And these were main actually friction with VC or investors who think, okay, this is it's a great technology, but it's not my thesis to invest in hardware, and especially with very long sales cycle times. So this is probably one of the biggest things that in the beginning, and we were very early as well when we started pitching for investments. And that's the other thing about hardware. Probably you need to get the right investors at the right time, when something kind of works, and not just out of university with half-baked, half-assed, something that doesn't really work.
And I know that you've been supported also by Venture Kick, or you were part of the Venture Kick program and then Kick Fund. In which way did that help or maybe even kickstart your fundraising journey?
So there are multiple stages with the Venture Kick, which eventually leads to the Kick Fund. Exactly. And so they were the right amount of money at the right time, because you're looking for this 60K to go from this early prototype to a manufacturable thing that you can put and get it to showcase it, or you need an extra 20K to go to Denmark to install on a prototype with a potential customer. So as long as you know where you want to use the money and how, then they actually came at the right time. And then what helped us in these early days is that we tuned our pitch. Our technology can do a million things, and that's what we were selling in the beginning as a pitch. But then, really, what does it do? What's the real value proposition, and to who? So if I'm paying, whoever is gonna pay for this one needs to get a value out of it. So who is that individual, and what is this value? Yes, because there's also a difference between pitching a technology versus pitching a product with a value proposition. Sure. So a technology can go in a million directions, and this is what we thought, we are very clever. We can sell this technology in this industry, in that industry, and that other industry, in airspace, and wind tunnels, in cars, and the wind energy. But we're starting with the wind energy. But yeah, that's great. It has a lot of potential, but let's show it first in real life with one industry. And this is kind of honed and tuned our pitch very early on with the Venture Kick Foundation, with the money that we received there, clearly.
And do you have any other programs or partners that you say really helped you in the beginning, like helping you grow, that have been instrumental?
There are definitely a lot of individuals, maybe without necessarily mentioning names, but Innosuisse with their different programs were very, very helpful, with a lot of different specialists that came, and at the right time with very specific aspects, either from an investing point of view or manufacturing point of view or simple administration point of view. So I would like to thank them. Yeah, of course, there are a lot of the pitching events in Switzerland, in Zurich, which is incredibly helpful. 99% of the time, you get nothing out of it except 2 or 3 people who really come and commend you or really like your product. They don't need to invest. They don't need to give us money. They don't need to do anything. Just give us some good, tap on the back and say, okay, good job. Or simply giving us access or introduction to another person. And there are a lot of these events in Switzerland. You just need to go out and do them and expose yourself. I'm very shy, but Iris is very good at that, so I delegated this to him, and he's really good. So he did a lot of the Venture Kick stuff. He was responsible for in the beginning, and a lot of pitching around. He also did quite a bit of that as well.
Do you have any tips for other hardware startups starting out in terms of, I don't know, funding, but also maybe in terms of energy, like how to make sure they keep their energy?
Yeah. So when it comes to hardware, depending on the hardware, but the most important one is that try to find a customer, and only one customer, and only one use case, and only one application, and build your hardware specifically for that. Don't be clever and then try to design it for efficiency or optimization. Just get it to work. Even if it's expensive, it doesn't matter in the beginning. But as long as it works, as long as it does what you say it does, and as long as the customer is happy, this will save you a lot of energy in terms of finding the most optimal components or the most energy efficient components or the best microchips or the best firmware. You don't need to optimize your firmware if you have 1 or 2 very specific applications for a specific customer. All the generalization can come later, all the optimization can come later, and all the clever design for manufacturing can also come later. So keep it really simple in the beginning. And this will save you a lot of energy and a lot of money as well. You don't need to have, because the moment you go into optimizations and big manufacturing, you need clearly a lot of people. So that's one thing. The other thing is not only have the customer, keep your product very simple in the beginning, even if it's expensive, it's okay, but also try to be on the factory floor where you're manufacturing the thing, because being a CEO is great, but if somebody asks you how does it work and you don't know, then we have a problem. So you need to get on the factory floor, put the chemicals, do the injection molding, stick the electronics. So it's very important to be on the factory floor with the people doing it, and be the person installing the thing at the customer, because you don't get very good feedback all the time. Especially if, be direct. Don't wait for your technician or the third party. Really be yourself. I had to be. Yesterday was one day. It was raining and wet and cold, and I was installing something on a blade. It's not fun, but at least you know how it works yourself, so you can go back and say, okay, we need to change X, Y, Z. So that's another thing. And the third, the final one is if you want to do hardware, talk to people who actually manufacture stuff, who ran hardware companies. There are a lot of people who give you recommendations, but they've never done anything in their life other than being in a corporate job. That's great. But when you do with hardware, you need to talk to people who actually manufactured and dealt with it. So that's very important.
And if you look into the future and you imagine RTDT a few years from now, what achievement would make you think we did it?
So we have a mission where we say we're building the best aerodynamic assessment system on this planet and any other neighboring planet. They don't exist, but you know. So if we have achieved where AeroSense for aerodynamic assessment interface with the control system of a wind turbine becomes a standard, like if you go to any company, they say, how do I do it? There's AeroSense. Then we've made it at that time. It's a concentrated market and we sell to B2B. So a normal person will have no clue what it will not be a Google thing, but at least those who know and in the industry will know, okay, there's a standard system, hardware and a software and an interface to the control system. And it actually does what it does and statistically proven on hundreds of turbines. So you have a very high likelihood that if you use it, it will give you the revenues. So the business case is very clear in that regard.
Super cool. Yeah. You mentioned before that originally you had it, or the product, for many different industries and surfaces maybe. What was like another industry that you would have like really loved to dive into?
Yeah, so it's real. I mean, now, because when you're a startup, you try to make money. So we also sold it to a university operating a large wind tunnel. And they have a very, very specific application where they needed to measure aerodynamics on, I would not say exactly what it is, on something. And that something is oscillating at very high frequencies. So they couldn't use classical, traditional aerodynamic measurement systems. So they wanted to use this. So we said yes, and they paid, and we're building it for them. Yeah. In hindsight, it's a lot of work, but you don't know until you know. Yeah. The other one is in the drone industry. So now there are larger and larger drones, utility drones. So they can, for not necessarily military use, but for, let's say, civil industry, transportation, they need to carry hundreds of kilos. And they look like helicopters, and they suffer from very specific instability. And then one project we were very close to do, and that's the miniaturization of what we have for the drones. Miniaturization relative, I mean, because these drones had a 1 meter rotors and there were 4 of them. So they're fairly large drones. So that's another industry, hopefully, maybe one day we could get into. And but another one where we are actually and getting paid is in the road industry. So Aris managed to sell AeroSense in India for a government entity, not measuring aerodynamics and measuring something else, but still. So we got there. We don't regret it, but it makes us money. But sometimes we need to, another thing is that we need to focus quite a lot. Because the wind industry is not easy, and measuring aerodynamics and working with control systems is not easy. Yeah. But in the early days, when you don't know what you're doing, you try to sell and you make some money, which is great. But now you try to, let's focus.
Yeah, cool. What are you most excited about that's coming next?
So hopefully very soon we will have some very nice contract with an OEM. We're actually stepping up from our software and really interfacing with the control system. Because in the wind industry, control systems are the holy grail. You don't touch them and you don't expose them to any external third party. So our clever bit is we have our own software that is analyzing all the aerodynamics and structural data. And there's the control system. And in between, we're creating a plugin or an interface that where both software are not supposed to know about each other. But essentially, this plugin takes our input from our aerodynamic analysis and interfaces with the control system parameter on the other side. And this, hopefully, we will get it done towards the end of the year. And if it works, then I think we're done at that point. Yeah. So clearly, you can start seeing. We have our now manufacturing, hopefully, partner coming up. So you can see that slowly things are getting into motion, into place. Things are getting manufactured. Yeah, we will have a lot of problems also in manufacturing. I have no doubt. A lot of issues in deployment, I have no doubt. But I don't look forward to this, clearly. So, yeah, this is it.
Yeah, that's exciting. I'm looking forward to seeing what happens at the end of the year and then in the next years.
Oh, so
And-
now you'll have to come back and
Exactly. We'll do another episode in a couple years maybe.
Yeah.
But before we finish up, we always do a round of rapid fire questions. So I ask you a question, you just say the first thing that pops into your mind. What's the most surprising thing you've learned from working with turbines?
that it's very difficult to get onto a turbine. And I'm not afraid of heights, but an extended amount of exposure to heights is not very healthy. In addition, yeah. Yeah, I was on a crane 2 summers ago. No problem, 80 meters up in the air. It's okay. But then the wind started to pick up and the thing started to sway at a hertz or 2 hertz. And I got motion sickness. I needed to throw up. So we had to go down. So, that's the most surprising thing. Otherwise, they're sexy machines. Yeah, really.
And what's one engineering tool you couldn't live without?
Maybe my brain.
That's fair.
Yeah, I don't know.
That's a good answer. I like it. If not wind, which renewable energy source would you bet on next?
Nuclear power. I think we have a lot of resources. I mean, there's also now thorium. I don't know if it will work out or not, but in China, it's been running for a while. But I think if you really need to have clean base load, nuclear is a very good idea. And a lot of people will hate me for this, but it's just a reality. And it's proven in many countries that it's very safe, despite the fact that there are issues sometimes. But
yeah. And then what's the best piece of feedback you've ever received from a customer?
Actually, we really trust your team because they could call us anytime. They can talk to us. We were available to them a lot of the time, to the point that the individual there, our main contact point, is that they thought, his team, they thought of us as an extended part of their team in a way. And that's a good point of trust. So it was not the product or what we did with them or for them. It was just us, which is really great. And I really appreciate it. We never get this human feedback or contact in that regard. So it was nice.
That's quite a compliment too.
Yeah.
Very nice.
Yeah.
Thank you so much for being here and answering all of these questions and sharing your story. I'm super excited to see, what happens next with RTDT.
Yeah, I will send you a letter to show you what happened with the control systems at that point.
Yes.
But thank you so much for hosting, and thanks a lot for the questions. And hopefully people will, learn one thing or two at the end.
We hope you enjoyed today's episode. If you did, you can support us by rating our show on Apple Podcasts. This way, we can reach an ever-growing number of aspiring entrepreneurs.